Bismillahirrahmanirrahim. Before we go on further, today I want to review what we have talked about so far. We talked about 4 special line segments or lines in a triangle and the 4 special points that they created. First, we talked about the perpendicular bisectors, and we suggested the perpendicular bisectors are all concurrent, and the point of their concurrency is called the circumcenter. And the circumcenter was the center of the circle that circumscribes the triangle like this. Thereafter, we talked about the angle bisectors, and we suggested the angle bisectors were concurrent, and the point of their concurrency was the incenter, center of the circle that is inscribed in the triangle. Now, the perpendicular bisector theorem was instrumental in deriving the circumcenter, and the angle bisector theorem was instrumental in deriving the incenter. If you recall, the perpendicular bisector theorem states that every point on the perpendicular bisector is equidistant from the endpoints of the segment. And the angle bisector theorem states that every point on the angle bisectors is equidistant from the sides of the angle. Then we talked about the medians, and we suggested that the medians were also concurrent, and the point of their concurrency was called the centroid. Now, the centroid was very special because it was the center of mass of the triangle, or the center of gravity, so to speak. The centroid was located 2/3 the distance from the opposite side. Point C is 2/3 the distance from point P, and this midpoint M3 over here. Another way of stating that is that if this brown segment was called X, the red segment would be twice as long, or 2X. Finally, we spoke about the altitudes and how they were concurrent, and the point of concurrency of the altitudes is called the orthocenter. Recall that it is the altitude or the height of the triangle that we use to calculate the area of a triangle, which is 1/2 the base times the corresponding height. Now, these points by themselves are very special and curiously interesting and beautiful in their properties, but this is nowhere close to their exquisite nature and some of the mysteries that surround these special points. There are 2 aspects of these points that we shall explore further, just because they're so intriguing and beautiful. One of them is called the Euler's line, and spelled E-U-L-E-R-S and pronounced Euler. And if you're like me, you're wondering why it's spelled Euler and pronounced Euler, but that's the way it is. And the question is, what would happen if you construct these lines, all of them, in one triangle? Well, something peculiar happens, in fact, if you construct a perpendicular bisector, the medians, and the altitudes in a triangle, and that will give us the Euler's line. So to construct an Euler's line, first we have to get a triangle. So let's make for ourselves a triangle like this. And the first thing we're going to need are the 3 perpendicular bisectors. So here's the first one. Ta-da! And then here's the second one. Ta-da! And then here's a third one. Ta-da! And as you can see, the 3 perpendicular bisectors of this triangle are concurrent. And to be sure that we have our circumcenter, let's create the circle from the center and with this radius right there. And as you can see, the circle circumscribes this triangle, and we can move the triangle, we can change the shape of the triangle, but nevertheless, the point D there will still be the center of the circle that circumscribes this triangle. Well, like that. Okay, so we have our circumcenter. Next, we need to find the centroid, which we get by connecting the vertex to the midpoint of the opposite side. So here's one, and here's the other one right there. And we really need 2, but since we're doing this, we might as well do this like this. So that is the centroid. H is the intersection of the medians, and that's the centroid. And finally, we need to find the altitudes. Now, the altitudes, if you recall, are lines that are perpendicular from a vertex to the opposite side, like this. That's the first altitude. From this vertex to this side, that's the second altitude. And from this vertex to this side, that's our third altitude. And let's find the point of their concurrency, or where they intersect. So and that's the point of their concurrency. Now, what's really remarkable here, and it may not be readily apparent to you, is that the orthocenter, which is over here, and the centroid, which is over here, and the circumcenter, which is over here, they're all concurrent. This segment, the red segment, is the Euler's line and has three important centers. It is the intersection of the perpendicular bisector, which is the circumcenter. It has the intersection of the medians, which is the centroid, and it has the intersection of the altitudes, which is the orthocenter. And no matter which way you turn this triangle, all those 3 points would be collinear. And that's quite amazing. It's not a coincidence. It is quite amazing that in fact these 3 points, which seem so distinct from each other, they're all actually collinear. They're in the same line. And that is quite, mathematically speaking, quite uncommon. And that's what makes this Euler's line very, very special. And another special property of the Euler's line is that it contains the center of the 9-point circle. Inshallah, we shall talk about in the future. Drawn here is Euler's segment, but the line that contains this segment is the Euler's line, and that's a very, very special line indeed. Until next time, as-salatu was-salamu ala rasulillah, walhamdulillahi rabbil alameen. Assalamu alaikum.